Hello friends, welcome to my YouTube channel. My name is Akash Bandi, section Astrostat, subject EPC, topic basic bias. Bias circuits beyond the basics. Bias circuits are fundamental building blocks in electronic designs responsible for establishing the optimal operating conditions for various electronic components such as transistors. While the basics of bias circuits are well understood, exploring more advanced configuration can unlock deeper insights and enable more sophisticated circuit designs. This series delves into an intricacies of different bias circuits topologies, providing a comprehensive understanding of their principles, equations, and practical applications. Introduction to bias circuits. Defining bias circuits. Bias circuits are essential for setting the appropriate operating point of electronic devices, ensuring their optimal performance and stability. They determine the quiescent state of a circuit, which is crucial for amplification, switching, and other fundamental electronic functions. Importance of basic bias circuits. Proper biasing is critical for the reliable operation of electronic circuits as it helps maintain consistent behavior, minimize distortion, and prevent damage to components. Understanding the principal bias circuit is a key aspect of effective electronic designs. Bias circuit topologies. There are several common bias circuit topology, each with its own advantages and application. In this series, we will explore the emitter feedback bias, collector feedback bias, and collector emitter feedback bias configuration, delving into their circuits, diagrams, equations, and practical uses and cases. Emitter feedback bias. Circuit overview. The emitter feedback bias circuit is a widely used configuration that establishes the operating point of a transistor by providing feedback from the emitter terminal. This feedback helps stabilize the circuit against variation in transistor parameter and environmental condition. Bias mechanism. In this circuit, the emitter resistor creates a voltage drop that opposes the base emitter voltage of the transistor. This feedback loop helps maintain a relatively constant collector current, ensuring stable and predictable operation. Advantages. The emitter feedback bias circuits offer several advantages, including improved temperature stability, reduced sensitivity to resistor, parameter variation, and the ability to set the collector current to a desired value through the choice of resistance value. Emitter feedback bias equation. Key equations. The emitter feedback bias circuit can be described by the following equations. Collector current IC is equal to VCC minus VCE by RC. Emitter current IE is equal to IC plus IB. Base current IB is equal to VBB minus VBE by RB. Emitter voltage VE is equal to IE star RE. Derivation and insights. These equations demonstrate how the key circuit parameters such as collector current, emitter current, and base current are related to the various resistor values and supply voltages. Understanding this mathematical relationship is crucial for designing and analyzing emitter feedback bias circuits effectively. Design consideration. When designing an emitter feedback bias circuit, engineers must carefully select the appropriate resistor values to achieve the desired operating conditions. This involves balancing factors like power, dissipation, thermal stability, and desired current level. Collector feedback bias. Introduction to collector feedback bias in engineering. In engineering, data collection is a critical component of the design, testing, and evaluation process. Engineers rely on the accurate data to make informed decisions about material, designs, and systems. However, collector feedback bias can significantly impact the integrity of this data, leading to flawed conclusions and potential project failures. Collector feedback bias. Circuit overview. The collector feedback bias circuit is another common configuration that uses feedback from the collector terminal to establish the operating point of transistor. This topology offers different advantages and design consideration compared to the emitter feedback bias circuit. Advantages. The collector feedback bias circuit provides a good temperature stability, low sensitivity to transistor parameter variations, and the ability to set the collector current to a desired value through the choice of resistance values. It also offers the advantages of a lower input impedance compared to the emitter feedback bias configuration. Bias mechanism. In this circuit, the collector resistor creates a voltage drop that opposes the base collector voltage of the transistor. This feedback loop helps maintain a relatively constant collector current, ensuring stable and predictable operations. Collector feedback bias equation. Key equation. Collector feedback bias circuit can be described by the following equation. Collector current IC is equals to VCC minus VCE by RC. Base current IB is equals to VBB minus VBE by RB. Emitter current IE is equals to IC plus IB, and the collector voltage VC is equals to VCC minus IC into RC. Derivation and insights. This equation demonstrates how the key circuit parameters such as emitter current, collector current, base current are related to the various resistor values and supply voltage. Understanding this mathematical relationship is crucial for designing and analyzing collector feedback bias circuit effectively. Design consideration. When designing a collector feedback bias circuit, engineers must carefully select the appropriate resistor values to achieve the desired operating condition. This involves balancing factors like power, dissipation, thermal stability, and desired current and voltage level. Collector emitter feedback bias. Introduction to collector emitter feedback bias. Collector emitter feedback bias is a technique used in transistor amplifier circuits to stabilize the operating point of a transistor. By applying feedback bias from the collector to the emitter, this method enhances the stability and linearity of the amplifier, reducing sensitivity to temperature changes and variation in transistor parameter. Collector and emitter feedback bias. Circuit overview. The collector and emitter feedback bias circuits combines the principle of both the emitter feedback bias and collector feedback bias configuration. This hybrid approach offers a more sophisticated and versatile bias mechanism, allowing for greater control over the transistor's operating point. Advantages. The collector and emitter feedback bias circuits offers the best of both worlds, combining the advantages of emitter feedback and also the collector feedback topologies. It provides the excellent temperature stability, low sensitivity to transistor parameter variations, and the ability to fine-tune the operating point through selection of resistance value. Bias mechanism. In this circuit, both the collector resistor and the emitter resistor creates feedback loop that opposes the base collector and base emitter voltages respectively. This dual feedback approach provides enhanced temperature, stability, and reduced sensitivity to transistor parameter variation. Collector emitter feedback bias equation. Key equation. The collector and emitter feedback bias circuit can be described by the following equation. Collector current IC is equals to VCC minus VCE by RC plus RE. Base current IB is equals to VBB minus VBE by RB. Emitter current IE is equals to IC plus IB. And the collector voltage VC is equal to VCC minus IC into RC, and emitter voltage VE is equals to IE into RE. Derivation and insights. This equation demonstrates how the key circuit parameters such as collector current, base current, emitter current, collector voltage, and emitter voltage are related to the various resistor values and supply voltage. Understanding this mathematical relationship is crucial for designing and analyzing collector and emitter feedback bias circuit effectively. Design consideration. When designing a collector and emitter feedback bias circuit, engineers must carefully select the appropriate resistor values to achieve the desired operating condition. This involves balancing factors like power dissipation, thermal stability, and the desired current and the voltage level across the circuit. Practical application of bias circuits. Amplifier design. Bias circuits are crucial for establishing the optimal operating points of transistors in amplifier circuits, ensuring linear and distortion-free amplification of signal. They help maintain stability and consistent performance across a wide range of input and output conditions. Oscillator circuit. Bias circuits play a vital role in the design of various oscillator circuits such as those used in radio transmitter, clocks, and signal generator. They help to set the appropriate transistor operating point to enable stable and reliable oscillation. Power supply regulation. Bias circuits are often employed in power supply designs to maintain a constant output voltage or current, even in the phase of changes in a load or input conditions. This helps ensuring reliable and consistent power delivery to connected electronic systems. Sensor interfacing. Bias circuits are used to condition the output of various sensors such as thermistor, strain gauges, and photodetectors. By establishing the appropriate operating point, this enables accurate and reliable signals acquisition for a wide range of applications. Conclusion and summary. In the conferences series, we have explored the fundamentals and advanced concepts of bias circuits, covering the emitter feedback bias, collector feedback bias, and collector emitter feedback bias configuration. By understanding the circuit diagrams, underlying equation, and practical applications of these bias circuits, electronic designers can unlock the full potential of their circuit designs, ensuring stable, efficient, and reliable performance across a wide range of applications.